Swayam Prabha. Digital India. Educated India.
So the last 3 weeks, we have been doing statics, and we looked at various types of configurations. We looked at particles, we looked at bodies, we looked at mainly the connected bodies, which usually are the difficult and which are our main interest. So I assume that now you are quite an expert in drawing the free body diagrams and analyzing it for the unknowns. We know how the connections are made and so on. So that is the fundamental thing. So that forms a basis for the next stage, the dynamics. So dynamics is our main goal. So wherein we also look at the motion of the bodies. So under the action of forces. So let's see. So we have done the statics. So then the dynamics part I kept introducing, but let's just put it anyway in a nutshell again. Dynamics, the several classifications. You know it. So kinematics is the study of the motion without the things which are causing the motion, like without any discussion of forces. So while kinetics includes the forces, and then we have particle and rigid body, and system of connected bodies. And then we also have 1D, we have 2D, and we have 3D. So we have several classifications, either here or here or here. So some people take 1D and consider all these things. They consider 2D and consider the kinematics kinetics, and then they go for 3D kinematics kinetics. Or you can even take the kinematics and do all these things one by one. So there are different ways of approaching. So what we do here, we really look at the kinematics obviously first, and we look at how to deal with the particle and rigid body and system of connected bodies. Essentially, we deal with 2D. Of course, 1D is too simple, though we might introduce, but quite often it is 2D, and which we will take up to 3D. Sometimes it's easy, sometimes the extension is not that simple, particularly with a view of rotation. So rotations in 3D are difficult to handle. So the 3D we will take it, 3D dynamics will take it up at the end, but quite often, though we extend sometimes to 3D, but essentially it is 2D. And then mainly it is particle, rigid body, and system of connected bodies. So let us deal with the kinematics. Kinematics will be simple for a particle. You have been hearing all these words right from your school days of your 9th class. So what we here we deal with is the position, displacement, velocity. Displacement and velocity are obviously connected, and acceleration. So these are the description of the motion. And so we might deal with the particle first. So all these things. And in the case of particle, what we have here is there are various ways of describing the position and velocity and accelerations. Always these things had to be with reference to a certain coordinate system. You cannot just simply say that it's moving. No, it is with respect to a certain coordinate system, which we assume it to be fixed. Okay. And with respect to that, we would like to get all the velocity and accelerations, right? So we would like to get these things from inertial frames. And then once you talk about the reference thing, reference coordinate system, one of the simplest one is the Cartesian coordinate system. This is the Cartesian description. So particle P is moving along a certain curved path. So what we have here is X, Y, and Z. And so this is the position vector. So let's write it here. So the position of a particle in the Cartesian system, if it is represented by R and as a function of time, at A. So each one of these things are functions of time. Here, since this is a Cartesian coordinate system, so I, J, K are basic unit vectors along X, Y, Z. So they are fixed coordinates. So if X, Y, Z axes are fixed, so obviously the I, J, K are given here are fixed unit vectors. So this is the position. So if you want to get the velocity, here each one of them are functions of time. This is the simplest description. And the velocity is obviously, well, I need not go all these things, but still for the sake of completeness, I'm writing it's a limit of delta R. Delta R is I just wrote delta R only just to show that it is the displacement in a small time. And so this is we take the time derivative of these things. So this is a product of X and I. So here, since I is fixed, so we need to take only the derivative of X with time, so which we can use the convention. You can put dots, which denote the time derivative. So this is the simplest one, and you can go once more. So here, I can even point out many of these things. So since you already know, so by any chance, if I, j, k are also functions of time, then not only we write dx by dt times I, we also have to write another term, x di by dt, which we would be doing it in the case of cylindrical coordinates or polar coordinates or even spherical coordinates, where the unit vectors themselves are functions of time. We will do that very soon. So this is the simplest description. So we can take one more derivative. And so this is how the things are described in the case of a particle's motion along a path like this one. So if it is going along this path, so at any time, so if x, y, z or even r, so they describe in a vectorial form. This is how we arrive at various. Okay, so this is simple. Let's go to, there are many other descriptions by which we can find out as function of time. There are other descriptions. The other description here is that if you know the path, the path is known. If the path is, so just for the sake of simplicity, we will, I'll describe it in 2D. So here, so let us say this is the path AB. So if the path is known in the sense that the y and x, so for P, y is given as a function of x. So if this is known, and if the particle is moving, so if x is as a function of time, so if x coordinate is changing with function of time is like this one, so this can be simple substituted into this one, so we can get y. Okay, so this is an interesting thing here. So that means that the path is known to us, while in the earlier case path was not known, and whatever you give x, y, z, so they themselves will describe the path. Okay, so the interesting part here is that to derive the relationship between the velocity and acceleration. Okay, so if this is p, let us say if you want to find out the, say if it is going to p prime, let me just draw it a little bit bigger. So this is p to p prime. So we say that it is delta r. So p prime is small vector delta r, while the particle is actually moving along this path. So if you want to get the velocity, so it is delta r by delta t in the limit. And delta r, and this is the path. So s is the, if s is the path, so particle is moving at some function of t. So as if you measure the s from here, some point a here along this path, okay, the path, the length, then if you know s as a function of time, so this delta r and this is delta s, so this is also equal to delta S by delta T. And what is the direction? So the direction will be along PP. And so along PP, so the velocity, the direction is along. This is the direction. So this is, you can even say that it is the direction of PP prime, the unit vector along PP prime, right? So this is the magnitude and this is the direction PP prime. So what happens here is that, interestingly, is that as delta R and delta S go to the limit, then this is unit vector PP prime will become tangent here. So in the limit, this becomes tangent. And this is the velocity here. So the magnitude of the velocity here, and this is the tangent of PP prime. So here so this vector PP prime in the limit is nothing but the tangent vector here for the path. So this is, we call it as ET. So the velocity is now ds by dt. So we can even write it now. So the velocity here is the magnitude, or let me write it as ds by dt times et. And this we call as the magnitude and et. Okay, so the velocity is in the direction of tangent and it's having a magnitude of ds by dt given by v here. Okay, so that means that if you know that some vehicle is moving along a known path, so if you know its speed, so that means that that magnitude here, what we show here, is nothing but the speed of the particle along the path, and et is the tangent. So the interesting part is the next step, where we need to find out the acceleration. So if you want to find out the acceleration here, so it is nothing but dv by dt, and here, so there are two terms here, both are functions of time. So we'll say that it is dv by dt and et and v and det by dt. This is because you can say that the tangent here, this is et and this is et prime. So it keeps changing the direction. So obviously it has a time derivative. Magnitude may not change, but its direction is changing. So it has a time derivative. So that's what we put it here. So let us try to simplify this one. So dv by dt times et and v det by dt. So this is the one which we need to understand. So what is that? There are a few parameters which we need to understand here about the path. Important parameter here is the radius of curvature. Okay, so maybe just before doing that, so one thing here is that so just like since this is a two-dimensional motion, so we need, so this is et, and we also prescribe another unit vector en, which is normal to the path of the curve here. And so et is a tangent and en is a normal to that. So, and then as you keep moving from here to here, so this is et prime and this is en prime. So both et and en are rotating as you go along the curve. So it depends upon the curvature of the path. Okay, so interestingly, so how much they have rotated? So it all depends upon what is the radius of curvature. So the radius of curvature, so this is, so if this is or extended, so this is some point C here, if they extend, so this normal here and this normal here at P prime, they intersect here, so that is the center of curvature. Okay, so En is in this direction, En prime, so they will intersect at C. So this is the thing. And during this small process, so we say that the angle subtended here will be delta theta in a small time, delta t. So particle P moves to P prime, and the angle En and Et change by delta theta. So that means that this En has changed to delta theta. The same thing with Et also. So if you look at Et, so this is angle something here, and this angle, this is some angle theta, and this becomes theta plus delta theta. So Et has rotated by a small angle delta theta, and En also has rotated by a small angle delta theta, and so that's what we have to find out the time derivatives. Okay, so here I'll draw them because these are only the directions which we are interested in. So that means that, let us say, this is Et and this is En. This is Et prime. So observe that the Et, which was in this direction, has taken the direction Et prime, and which has rotated by an angle delta theta. And similarly, En, so has rotated through to En prime, and here also we have the angle of rotation delta theta. So this has rotated through a delta theta, this also has rotated through the same angle delta theta. Okay, so these are all related. So okay, so the change in Et, because that's what we want here, delta Et by, so this is nothing but limit of delta Et by delta t. All right, so what is delta Et here? So this is the one. This is the change in delta Et to get Et prime. So this is the one what we want here. Okay, so what is delta Et then? So this is nothing but a small arc. What is the size here? Unit. So when 1 unit circle with radius 1 unit rotated through, then the chord is nothing but the magnitude of this, nothing but, so delta Et, the magnitude of this one is nothing but 1 into delta theta. Okay, and then what is the direction of this delta Et? So in the limit, so if you look at this one, in the limit, so this becomes, as when delta theta starts becoming smaller and smaller, so this one will become normal to this radial line. So this becomes normal to this radial line, and that is nothing but in the direction of En. Okay, so the direction of Et, delta Et, in the limit is in En in the limit. Okay, the limit. So let me just see if it is gone. So that's what it is. Okay. So finally, what is delta ET then? So delta ET, if you want to write it completely, I'll write it here. So delta ET, this vector, its magnitude is delta theta, and its direction is En. And if I divide it by delta t, okay, so it becomes delta theta by delta t and En. Okay, so this is what it is. So interestingly, though I don't need it right now. So what is the change in delta En? Change in delta En, the En is this much. So this is nothing but delta En, change in delta En. So this magnitude is also same as 1 times delta theta, and this direction in the limit is opposite to Et. Okay, so delta En is nothing but delta theta times Et with a negative sign. So we don't need it right now, but this is what we want. So this is the one which we still have to explore a little bit, because this comes very often now. So I will write it again here. So acceleration, which we need to. So it's nothing but dv by dt times the direction of et, and this det by dt in the limit will become d theta by dt times. Okay, so I hope this simplification. So this is nothing but v det by dt is nothing but d theta by dt. So that means that time derivative of theta. So how theta is changed? So that is the important part here. So let us investigate this part here. So we have to bring in another term here. This one, maybe I'll just do that here and before. So it is dv by dt and in the direction of et, and this one I will write, I'll introduce another term ds. So what is ds? So ds, if you go back to this one, so if you are here, so pp prime, so this is the ds, right? So I have introduced the ds, so ds by dt. So what is ds by dt? So ds by dt is nothing but the magnitude is nothing but the velocity itself. So what essentially that is left is to find out how theta is changing with s. Okay, so this is nothing but v, and what is d theta by ds? So that is the one. So that means that if you look at this one, so this is what we want. Okay, we want delta theta by delta s. So you know what is that? So this is a small arc length, and this is the angle theta. So this arc divided by the angle, or the angle multiplied by the radius, is nothing but going to give you the delta s. So you know this one, the radius of curvature. So this is the radius of curvature rho. So the relationship between this delta theta and delta s is nothing but the radius of curvature r. So since we need it here, so let's write it as so in the limit. You can write it in the limit. I'm not writing that every time. So what we need to find out is that as particle moves along the given curve, so because we also know y is a function of x given to us. So what we want to do here is, let us say the tangent here is theta and the tangent here so obviously this will be theta plus delta theta. So the tangent at P is theta, this is theta by delta theta, and that same delta theta is reflected here. Okay. So if theta is the tangent, the slope of the tangent, so let us get some relationships. So this you must have done in your calculus to some extent, but for the sake of completeness here, so I'm just doing it. So what it is now, the relationship between slope. So slope is nothing but tan theta is dy by dx. Okay. So differentiating with x. So what we get is that theta is a function of, so it's d theta of tan theta okay. So this is secant squared theta, and we will write it as we'll introduce another term here. We'll bring in s here. So this is nothing but your 1 plus tan squared theta, and this is ds by dx and d theta by ds. So this is nothing but your 1 by rho ds by dx. So in the limit, so ds by dx we can write so delta s by, so something like, if this is delta s, delta x and delta y, so this is nothing but delta x square plus delta y square. So this is nothing but the limit so under root. Okay, so ds by dx will become 1 plus dy by dx square under root, and then this is 1 plus tan squared theta. So finally what we get here, so if you do all that, so then this becomes 1 by rho. So 1 by rho will become d square y by dx square, and this is 1 plus tan square. So this is 1 plus dy by dx square, and this part is this much. So what we get here, so they will be combined. This is 3 by 2. Okay. So this is nothing but, if you want, I can write it here. Okay. So this is the formula for your radius of curvature, okay, 1 by rho. And so going back then to the acceleration. So getting acceleration, so this is nothing but dy by dt, or you can write it as v dot t, and this is d theta by ds. So that's what we said. So this is d theta by ds, and that's 1 by rho. And so we can even write it as 1 v by rho times E. And another v, right? Yeah. There's one. Let me go back to the previous one. I missed one term there. Okay, so there's a one v here that's missing here. Okay. Let me just see. And this is, if you remember, so this is what this was, theta dot En. And so there is a v, so there's a v here. And okay, and so finally this is your quite familiar. So if the path of the particle is known, so then the total acceleration is how is the velocity changing along the path. Okay, if it is speeding up or slowing down, so that's the tangential component. And then this is v square by rho, so this is the times En. So this is also quite familiar to you. Now we went through a rigorous calculus approach, but this is nothing but if a particle is going along a circular path with velocity, speed, velocity v, and if you know the radius of curvature here, so you know that there is a centripetal acceleration, and so the centripetal acceleration here is known as v square by rho, right? So I'm sorry, v square by. So this is what usually you are familiar with. So whenever a particle goes along a circular path of radius r, so there is a centripetal acceleration towards the center, which is given by v square by rho. So that is what we are putting it in the vectorial form here. So there is, if the velocity itself magnitude is changing, so that is reflected as a tangential component, and velocity by itself, even if it is not changing, so there is a normal component here. Okay, so this is a very useful and in the vectorial form. So once we have gone through this one so elaborately, then the next one is another description is the cylindrical coordinate. So the description of motion in cylindrical coordinate consists of x, y, z, so where and earlier it was x, y, z. Now in the cylindrical coordinates, so we have a vector r in the xy plane, that is the projection of P here, say Q. Q is the projection of P on this XY plane. And so this is vector R. And this angle, if you call it as theta. So that means that this, the position vector R here is given by the distance R times, I'll tell you what these are. And then the one that is perpendicular is, so we have the projection Q is represented by the vector R, and then the third direction, the Z direction, is given by Z. So that's what we present here. So this is the two-dimensional representation of the projection, and this is the third direction in the Z direction. Okay, so here this is the description, and if you just look at this part is easy, and so if you just look at this, is we call as R. So this is the polar coordinates here. So where there is a R here and angle theta here subtended with. And so the position vector here is given by R times ER. So what is ER? So ER is nothing but the unit vector in the direction of R. Okay. So again here, interestingly, so this also comes under the, that if you take the velocity here, so dr by dt, so you take, this is the product of R and ER, so we have R dot ER and then R dot dER by dt. Okay, just more or less following the lines of your curvilinear the path known description. Okay, so this is, so that means that if there is a change in this length of R, so that is reflected in AR. And then what is this one? So that is the one which we need to, so this is R and this is ER and this is theta. So here again we introduce two unit vectors, ER and E theta. So it is ER in the direction of R, whereas E theta is perpendicular to ER. We call it as E theta in the sense that when theta increases, then the point P here moves along this one. And so that represents the angle, I mean the unit vector theta. Okay. So without, so if the path is going like this one, P to P prime, so this is P prime here, and this is delta R. And you can see that here, the ER prime and E theta prime are changing, so by an angle of delta theta. So if this is delta theta, looks now very familiar to you. And okay, just I'll conclude this one. So here ER has gone to ER prime. So the change in the vector delta ER is given by this small segment. So the magnitude of that segment is nothing but this 1 multiplied by delta theta. So this delta ER, which I'm written here, so its magnitude is 1 times delta theta. And now you can guess what is its direction. So its direction, this one, in the limit will become the direction of E theta. Okay. So in the limit, it becomes E theta itself. So that's what, so we can write it as R dot ER and R times DER by dt. So from that, we know that it is delta theta by delta t times E theta. So it's R dot ER and this is R theta dot E theta. Okay. So this is a polar coordinate formula in 2 dimensions. So you can see here that delta theta by delta t in the limit will become d theta by dt. So that means that theta dot times. Okay. I think I'll stop here.